All right, so let's resume from where we left off, actually. So today we will talk about, well, we transition from, we've been talking a lot about the memory. We're talking about the cache, the virtual memory, and the DRAM. Now that that's kind of done, right? Right now we are gonna transition to the next topic, which is GPU. Right. But before we go there, I'll first quickly talk about a few more things, which is the VLIW, which is one of the major architectural design that kind of basically look back at what we learned so far, right? So if you look back at the topic for our midterm, you've been seeing things like out of order scheduling, which involve out of order instruction dispatch. Basically, it means that you would dispatch instruction not in the same order as their arrival, right? So you issue instruction whenever the source is ready. And this can be done through multiple components, right, that are being added, things like instruction windows, reorder buffer for future file, or the combination of the future file and architecture of register file, right? And then these are done so that you can have a much faster CPU, right? And also this can be done so that they can be tolerating the latency of the instruction that can take a while to finish, but they also come at a cost, right? Things like reservation station, which acts like a huge buffering area for your instruction, right? This scheduling windows requires wiring. It requires logic so that it works the way it's designed to. You also have the reorder buffer. You have the structure to basically make sure that whenever you want to finish an instruction, they are still in the same order, right? So that from the programmer point of view, there's no surprises. You would have the register aliasing table or the register rename table to support register renaming, essentially, right? And in this case, right, when you have register renaming, the IDs can be renamed to the reservation station entry, right? The information in there would include the tag, the value, and the valid bit. Basically, kind of go back to the midterm, look back at the question about out of order execution, and basically that's the overhead right now, right? This is like there's a lot of benefit here, right? It's good because it eliminates right after read and right after write. And it's kind of virtually, right, enable the performance of having so many more registers, even though the ISA only support a few physical registers. And we talk about the Tomasulo algorithm, which we're not going to go into the details. This is just a quick recap. So if you want to review the slide, it's there. All right. Then we need to have a side discussion on the language itself, right? Because programming language offer different benefits. So one example is, let's say you program in C, right? You have the benefit of having a really low level programming language. C++ gives you the benefit of having object-oriented programming. Python gives you the much more abstract way to like define things and quickly write a script to run your program. Java, also like standard ML, basically all these things like Haskell, functional programming provide different benefits, right? They comes with certain flavor. And these programming language has trade-offs. Some of them are more friendly toward von Neumann architecture or the execution model, right? Some of them are more friendly toward data parallel that is friendly toward the GPU. These are the language like CUDA, right? Also a language that have a pretty well aligned with the data flow model, which are things like functional languages, right? So functional language are more friendly to a data flow model because basically in the data flow model, things are fire off as soon as the operands are ready, right? Some of these are easy to write, some of these are designed so that it's easy to parallelize, easy to make it fast, all right? You also have the execution model. Execution model basically is governing for different programming model. The hardware can use a different way to execute things. It can be doing things in in order, out of order, using vector processor, array processor, data flow processor, or even multi-threaded processor as we know it, right? This execution model can be different than the programming model. For example, your CPU support out-of-order processor. These imitate data flow model but run von Neumann. Basically, your program is von Neumann, but it actually executes and imitates the data flow model during the execution, right? You also have the compiler. So basically, the compiler compile your code. You can have code, then it translates to intermediate representation. Then you optimize the assembly, and obviously, compiler will optimize your code. Basically, try to understand what is your program. Then it reshuffle things inside your own program automatically while you're compiling, so that it runs faster. It can be used to find parallel code. It can be used to find independent instructions, so you can shuffling them to make sure you make the better use of the out-of-order processor. It can be used to find loops and then unroll the loop automatically to even like improve the speed of your program, right? You can also try to automatically vectorize parallel code, even find bugs, right? Anyone ever check the warning when you compile the program? Those are potential bugs, right? The compiler detects it and say, hey, that part of the program looks sketchy. Look at line number 100. That part seems sketchy. Please look at that. That's the compiler job, right? So with all these things, out-of-order scheduling, compiler, programming language, now you have a design, well, I wouldn't say design issues per se, but something you want to think about in terms of the design, right? So, for example, if you look at out-of-order processor, it requires a huge amount of hardware support. It needs a large instruction windows. These are complex and costly, right? These are done to support, if you will, the ability to perform scheduling, to perform dependency checking, and to support the data parallel. Basically, add as much data parallelism as possible. These allow you to execute a lot of things in parallel, access a lot of memory location in parallel, right? Back in the day, if you look at the processor invented in the 70s, for example, we don't have that many transistors. So your trade-off is you're going to spend a lot of transistor implementing this thing or make it cheaper. For example, you can do decouple access execute because out-of-order is complex. The idea is, well, can be separate out your program into two different streams. The first stream is just instruction that do computation. And the second stream is the instruction that just want to access data. So you have the access stream and the execute stream. This is a paper proposed in like the 80s, and it's there to address the overhead of out-of-order, basic out-of-order scheduling to make it cheaper, right? The compiler job is there to generate. Basically, you write a program. The compiler compile your program. Instead of having one assembly that the CPU run, it generates two separate code. The first code only involves data load and data store. Anything that has to do with accessing the data. The second stream will just do anything that has to do with computation of the data. And there'll be synchronization. Once you load this data, send it here, execute, send it back. And here are the rough diagram taken from the paper, right? So you have the memory, you have the execute instruction coming in to the execute processor, right? So let me change the pointer to laser point. So it goes in here. The execute processor perform computations. It has a queue that say, okay, if I have the input from the access stream, which basically do the data read and write, so I can read something from the memory, feed it here, I perform execution on that data. Once I'm done, I send it back, write the data back. So you have the write queue, you have the execute to access queue, you have the access to execute queue. There's a synchronization between the two queue, right? And these are there to, again, becomes a barrier and synchronization between the two, basically the two stream, if you will, stream of instruction, All right. And the trade-off here is obviously the execute stream can run ahead of the access stream. The access stream can also run ahead of the execute stream. Basically, this is like a lower overhead of out of order. I just keep executing things. I just keep accessing things if I can. I'll try to get a lot of things into your processor as soon as possible, but it's streamlined into a decoupled execution manner. The problem with this is, it's not a problem per se, but the overhead here is, well, someone needs to design the compiler. So the compiler is responsible now for making the two streams. And code branches becomes a bottleneck, because if you go back one slide here, right, you see that this is basically the queue that handle branching. The branch queue becomes another serialization bottleneck. You cannot really just do branch prediction or whatever in this particular architecture, right? So that's the downside here. Now, that's the DAE architecture. Is there to make the, I would say, postman version of out-of-order scheduling. Basically make something that imitates out-of-order processor in a cheap way. Okay? Rely on a compiler to generate the code for you. The code in theory should be kind of correct, well, by default correct and high performance, right? Then if you look at how you would fetch the instruction, right? In out-of-order processor, you keep fetching, fetch. They are staying in the instruction window before you can be dispatched. There are going to be a bunch of many basically ready instruction, and the scheduler pick what to issue, right? So there's a lot of ideal choices. You can look at the data flow graph, try to detect and see what are the critical instructions that go first, things that are most likely to be needed or have many consumer, right? But what if I change the way I think about instruction stream and say, hey, what if I add a lot of ALUs? I have a few adders, a few multipliers. Can I fetch an instruction that say I want to do 2 add, 3 multiply? Again, the idea is, let me recap in Thai. ก็คือสมมุติว่าผมดีไซน์ processor ปกติแล้วผมก็เพิ่ม ALU มีตัว adder 2 ตัว multiplier 3 ตัวเงี้ยแล้วผมก็กลับมาคิดใหม่ว่าเฮ้ยถ้างั้นอ่ะถ้าเราทำให้ instruction เราสมมุติเรารู้ว่ามีตัวบวก2คูณ3เงี้ยแล้วเราสามารถ fully pipeline พวก ALU พวกนี้ได้ถ้าผมให้ instruction เข้ามาใช่ป่ะแล้วผมบอกว่า instruction แต่ละอันอ่ะมันจะเป็นการบวก2 อันคูณ3 อัน by default ผมก็จะได้ throughput เยอะขึ้น so if there are multiple types of ALU I can think of fetching the instruction this way by packing those ALU into one single instruction, right? So the question to ask is, well, again, there's multiple type of ALU. I want to maximize utilization. I want to keep squeezing in performance, right? The main problem is, how do I do that? How do I do the scheduling? It can be complex, right? So you need to kind of model the dependency between instruction, what has to finish first, what has to finish afterward. And you need to figure out what can be scheduled together, right? And a typical out-of-order processor is you're going to have large instruction windows that do a lot of complex dynamic scheduling. So the hardware performs scheduling. Again, การดึงว่า instruction ไหนจะไปก่อนจะไปหลังมันถูกทำโดย hardware สำหรับ out-of-order processor นะครับ Here comes VLIW. Assumption here, compiler are awesome, right? So quick assumption about VLIW, we would rely on the compiler to do more things. Okay, so far we learned about dynamic instruction scheduling. Out of order, the hardware try to maximize everything on their own, right? On their own. Now, the downside is you have limited instruction windows, you have complex scaling logic because the hardware becomes a scheduler, right? Another different idea, I can do static instruction scheduling because fundamentally instructions that are ordered in memory are already ordered by a compiler. So a simple compiler would try to basically convert your code into assembly that reflects your code. But a more complex compiler can try to reorganize and shuffle your code in a way that is more friendly toward your hardware. So for a quick recap on acyclic graph, right? So a direct acyclic graph means that it's a graph with direction. So I can use this concept to build a dependency graph, right? I can use it to build a dependency graph. So let me draw this a bit. All right, let me pull up my tablet here. All right, so I can use a graph to represent instruction. For example, if I know, right, if I know that I have an add instruction, I have to do A plus B, right? I'll just do A plus B, right? Another instruction would do the multiply. C multiply by D. And then I need to multiply the result of these two, right? And then there's another independent instruction that do an add, that do A, again, same input, and C, right? And then I want to take this output and add them together. This is a graph. Basically now, essentially this becomes a graph, right? You have dependency. Something has to be done before other steps. But at the same time, you also see parallelism. The first level here, as you can see, add, multiply, add, can be done in parallel, right? So if you can compile your code and build this graph, it also means that you know for each of the steps, in this case, for example, in the first step, if I have two adder, one multiplier, I can do all of them in one go. All right. And going back to the concept of instruction word, right? Instruction consists of opcode and operand and many other things, right? So the thought experiment here is, well, what if I just pack multiple instructions into one? Instead of having one instruction that do an add, I have one instruction say is to add, one multiply. What if I can do that? The benefit is the scheduling is done through the compiler, because the compiler now need to figure out, I have to add, one multiply. How do I figure out two independent add and one independent multiply and do it here? It allows the compiler to pre-pack a set of things that you can do, right? So that's basically the concept of VLIW, or very large instruction word. All right, so the idea is I want to create, well, I want to build a CPU with multiple functional units that has multiple types. And then I'll rely on a compiler to find independent instruction and squeeze it into one single instruction. So each group or each bundle are instructions that execute in lockstep. When I said execute in lockstep, basically means that they get launched together. And instruction within each group, right? Instruction within each group are statically aligned to directly feed into the correct functional units. To feed into functional unit, if you cannot find independent instruction, you just say in no ops, right? One example of this is proposed in 1983, basically called very long instruction word architecture for the ELI 512. ELI stands for enormously long word instruction. This is one of the high impact paper that kind of proposed like a functional architecture that do 512 bits instruction. And here is the high level design, right? So let's say you have the program counter pointing here. That's your instruction. That's one single instruction. In that case, right, you have 4 processing elements. The first one can add, the second one can load, the third one can multiply, the fourth one can do the move instruction, move between one register to another. In that case, you just need to find and make sure, the compiler will make sure that the first slot is adding, the second slot is dealing with data access, the third slot is dealing with multiply, and the fourth slot is dealing with register movement. Has to be aligned and make sure it goes to the correct type. All right. So now let me explain VLIW again in Thai. โอเคนะครับก็คือมันชื่อว่า very large instruction word การทำงานของ VLIW architecture เนี่ยก็คือเรา add ตัวบวกลบคูณหารไปเยอะๆตามที่เราต้องการแล้วเราก็จะตีต่างว่า compiler อ่ะมันจะสามารถสร้าง instruction ขนาดใหญ่ขึ้นมาที่บอกว่า instruction อันนี้จะบวก1อันคูณ1อันอะไรก็ตามแต่สมมุติว่าใน CPU เราทำบวกได้2ตัวคูณได้2ตัวพร้อมๆกัน compiler ก็ต้องไปหาโค้ดแล้วบอกว่ามันจะ pack instruction เนี้ยว่าต้องบวก2คูณ2ต้อง align ต้องทำเป็น lock step ก็คือทำไปด้วยกันนะครับแล้วอันนี้เป็นหน้าที่ของ compiler ที่ต้องไปหา independent instruction มา fit in ถ้ามันหาไม่ได้มันจะใส่ no op no op แปลว่างั้น slot นี้ยังไม่ต้องทำอะไรใน cycle นี้ใน instruction นี้ก็จะไม่มีอะไรเกิดขึ้นก็คือ throughput จะลดลงนะครับ so that's the concept of VLIW. Alright, so the discussion, obviously there are trade-off, right? The complexity, hardware is simpler. From the hardware point of view, I don't have to do much. I just align the lane and then I feed the instruction correctly. That's it. The compiler is way more complex. The compiler is going to be way more complex because I need to search and see where are the independent instructions to feed it in. The programmer also have a tougher time because I can, well, it's a room for optimization, but I need to know the hardware enough so I can optimize the code correctly, right? But if there's branches, then you throw away a lot more things, right? So branches are even worse here. And you can see the example in GPU world as well, that branch are bad for these types, I guess, this school of thought in terms of architecture. What if the program are not parallelizable, right? That's also another possibility. You have an example of modern VLIW processor in the Intel Itanium the 64-bit version from Intel. In the Itanium processor, it died, all right? Intel discontinued this by now. But it's been there for quite a long time. It does use VLIW. It's not fully VLIW, but it does have the instruction set that follow the same principle called the epic instruction set. This architecture from Intel allows dependent instruction within the bundle, so you can kind of have dependency, so it's easier on the compiler. You can add bits to extract the dependency. It kind of failed due to backward compatibility, because if you extend the 32-bit version into this IA64, your program doesn't work. You can kind of fundamentally use the compiler to fix the problem, but at the time, the market adapted to the AMD variant for the 64-bit processor. So that's kind of what happened back then, all right? So that's a quick recap on VLIW. Now, let me take a quick break because we're going to transition into another set of type of processor that some of you call it vector processor or array processor. It does have some similarity, if you will, to the VLIW architecture as well. This is called the graphic processing units. All right, so stay tuned. We will be back in 5 minutes.